Hi everybody, so let's continue on with our discussion about collisions in terms of kinetic energy and momentum. So we're going to look at the last case, which is perhaps the most important case and the most complicated, and that's perfectly elastic collisions. And I want to make sure we understand what perfectly elastic means, because when I first introduced the idea a chapter ago, I gave you a imperfect definition. I basically said when two objects collide, they don't stick together. Well, that's not really a good definition, because two objects can collide and separate, and it can still be partially inelastic or partially elastic. So we want perfectly elastic. So before I get into that, I'm going to show you a little demonstration from a simulator, and I can also show you in class. And this is the classic Newton's Cradle. Okay, you've seen a device like that where you have three, or in this case 5 spheres that are all the identical mass hanging in a pendulum. And what I can do is I can pull one of these back and let it go, and it's going to collide. And the question is, what's going to happen on the other end? All right, so you may have seen this before. So I have one coming in. Will I have one going out? Will I have two going out, three, or will all four move? All right, so pause this, make a prediction, and then we'll talk about it. Okay, so we have one goes in, one goes out. Question is, why? Why don't two go out, or three go out, or all four go out? From a conservation of momentum standpoint, we can understand if one comes in, one goes out with the same momentum. Okay, but why couldn't two go out with twice the or half the momentum and still conserve momentum? All right, so conservation of momentum is not a complete description of what goes on. So if I pull two back, I get two going out. And if I pull three back, that's odd. You might think just the two will go out with an extra high swing, but three go out, and then you can see a pattern developing. If I have four, you think four coming and colliding with the little red one, the lonely red one, that red one's going to go flying off, but it doesn't. So there is another law that's governing this behavior besides conservation of momentum, and that's what we want to look at. All right, so let's go back to the all right, so sorry, anyway, so in the other examples, we looked at situations and asked, is kinetic energy conserved or not? And that was for inelastic collisions and explosions. So a perfectly elastic collision, we're not going to derive it from that way. We're just going to come out and say that in perfectly inelastic collision, not only is momentum conserved, so in all situations momentum is conserved if there's no external forces, but kinetic energy is conserved as well. So there is one type of collision where kinetic energy is conserved, and that by definition is perfectly elastic. So keep that in mind. Perfectly elastic goes along with this statement. And so if we go back to Newton's Cradle, we can explain why we didn't have, let's say, for example, one ball go in and two or three leave with half the momentum. Schematically, here it is. So if I've got mv coming in, why can't I have 2m go out, 4 and 5, with half the v, right? So 2m multiplied by v over 2 is the same as mv, which matches that. So in other words, 2 could go out and still conserve momentum, but we never see that. We only see 1 go out. And so the answer to that is, because this is a perfectly elastic collision, we also have to conserve kinetic energy. And so let's show why it's not conserved when you have more than one sphere go out. So based on conservation, so I've already kind of done number one, solution. Based on conservation momentum above, definitely yes, you could have 2 go out. Okay, and you can see in the spaces below how I've shown that the total momentum before is mv, and if 2 go out with half the speed, we still have mv. So there's no problem there. All right, now let's look at kinetic energy. Is that conserved in that case? So if 1 comes in and 2 goes out, with their speed is v over 2, right, and a mass of 2m. Sorry, I just got lost here. All right, so what's our initial kinetic energy? Well, 1 came in, so we have 1/2 m and whatever velocity, I'll call it 1 squared. Afterwards, if I have 2 go out, I have 1/2 still, 2m, and then I have half the speed, but I've got to square it. And so if I simplify the whole thing on the right, 1/2 cancels out with 2, I've got mv squared all over 4 because I have to square this 2 right there, whereas here I have mv squared over 2. So what we see is kinetic energy is not conserved. And since this is a perfectly elastic collision, which means it has to be conserved, then you cannot have one ball go in here and 2 come out. The only way to conserve kinetic energy and momentum is if 1 comes in, 1 goes out. 2 go in, 2 go out, 3 go in, 3 go out. So that ultimately explains the results of Newton's cradle. Okay, so I've already explained all that. Now, a more difficult problem. How do we determine the final velocities of 2 objects when they collide elastically? So I'm going to do a derivation here. So the good news is you don't have to know the full derivation and even the result, but I want to show you for completeness because it's a neat solution. Okay, so let me explain this a little bit in more detail. So suppose I have 2 generic objects, A and B, that are going to collide, and they're going to collide elastically. Let's remind ourselves of that. They could be moving towards each other. One could be stationary. The other one, they could be moving in the same direction. It doesn't really matter. And so ultimately what we want to do is if we know this and know this, we should be able to predict both of these. If we only have conservation of momentum, we cannot predict the individual momentum. We can predict the total is going to be the same as the original, but to get the individuals, there's 2 unknowns and we have 1 equation. So if we want to ultimately be able to predict exactly how 2 objects can behave after without having to measure 1, which we did prior, then we're going to need another equation. Now, other equation is going to come from conservation of kinetic energy. And when we combine the 2, we have 2 equations and 2 unknowns. So I just want to show you how we would set that up and what the final solution is without getting bogged down in the algebra. So if we want to figure out both this and this, an equation, we want to start with conservation momentum. So sigma p equals sigma p prime. So we just got to break it down. So we have MAVA plus MBVB, right? There's our total momentum before the collision, must equal MAVA prime plus MBVB prime. Okay, where our goal is defined, again, we want an equation that predicts this and this. So right now we have 1 equation, 2 unknowns. We can't get anywhere. So like you learned in math, if we want to solve that, we need another equation. So let's go to conservation of kinetic energy. Sigma k E must equal sigma k E prime. And again, this only works if it's perfectly elastic, which is our situation. So now I have to, it's a little bit more of a pain to write, one half MAVA squared plus 1/2 MBVB squared has to equal 1/2 MAVA prime squared plus 1/2 MBVB prime squared. Ooh, what a pain to write. So this simplifies a little bit, and the half cancels out because it's in all the terms. So the goal here is algebraically, and I challenge for those of you who like a nice math challenge, to solve for VA and V prime. Okay? So what I have to do is combine these 2 equations. I'll give you a hint how to do that. It's not so easy to just solve for VA or V prime and substitute it back in the original equation. It becomes a mess. So what you want to do is move all the A's and B's to one side. In fact, I'll do that step for you right now. Okay, so if I move all the A's to one side of the equation and all the B's to the other side, it makes it a little bit easier. So what I can say, without getting too bogged down in the details, so I'm just going to move up here because that's where I have space here, is I can say MA, and I'm going to factor out the MA, VA squared minus VA prime squared is going to equal MB, VB prime squared minus VB squared. Okay, so you can factor this out to VA minus VA prime. Sorry, my handwriting's getting all messy here. Let me say that again. I can factor this to VA minus VA prime times VA plus VA prime. And I can do the same thing over here. I don't have space to write that. And then what I can do, and this is the neat thing, and I'll let you try it on your own if you want, I can take this whole mess that I've expanded and divide it by this, and I can get a bunch of things that cancel out. Anyway, voila, with a little algebra, if you actually follow through, this is what we end up with. All right, it's a long, complicated equation. You don't have to know it. You're not going to have to really apply it. But let me just show you how it predicts something that we've seen before, way back when we were doing collisions. So let's say I have the following situation. Let me change this. This is not what okay, so yes. Yep, I got to make a slight little, nope, modification is, and I think yours is written a little bit differently than what I have here. I believe yours has a B here, A here, a B here, an A here, and a minus sign here. Anyway, let's say we have a situation where I have object B coming in, right, as drawn here, and it hits a stationary A. And we want to predict how B is going to behave after. And so we can look at three situations where we can look at the relative masses. What if A and B have the same mass? Well, if I'm looking for how VB prime behaves, if A and B have the same mass, then this term right here adds up to 0, and this is already 0, so I get 0. So in other words, VB prime must just be 0. In other words, when an object hits another object of the same mass, and it's perfectly elastic, the first object has to come to a stop. On the other hand, if A is less than B, okay, so A is small, B is big, we already know B is going to go forward. And if I look at this term right here, if MB is bigger than MA, then this term is positive, and so I'm going to have a positive result, which means that VB is going to keep moving forward. And if B is smaller than A, then this term right here is negative, and it's going to bounce back. So that ultimately predicts why objects behave like that. Alrighty. The last one, this is a huge one, okay? A ballistic pendulum. We are going to do a lab based on this, so in essence, I'm doing the theory for you right here. So let's understand what a ballistic pendulum is. I have a pendulum where I have a block at mass m, and there's a cavity in it. And that cavity is there to catch an incoming projectile, a bullet, if you will. And so here is our bullet coming in with a velocity v. So when the bullet comes in and hits here, it collides, and because this is a pendulum, it swings up, and it swings up to a new height, or it swings up to an angle. We can relate angle, height, and I can add in here the length of the pendulum, but that's a derivation I'll save for another time. Okay, that's just trigonometry and a little bit of geometry. So our goal is, if we do this event, we can measure this angle. We know the mass is involved. So what we ultimately want to figure out is how fast must the bullet have been coming in, such that when it collided with this block, it swings up to this angle. So to do that, this is a collision, and we got to consider conservation laws. And once we understand what the conservation laws are, then we can apply the appropriate equation. So I'm going to establish the conservation laws, and then I'm going to ask you to try to do the following, okay? It's a good exercise for you because you have to do it for lab anyway. So there's two events, and that's what we have to make sure we distinguish. The first event is the actual collision, and then the second event is the swinging up afterwards, okay? So we have to ask ourselves, is momentum and kinetic energy conserved in each of these events? So let's look at the first event, the collision between the bullet and the block. Is momentum conserved? To answer that question, we just ask ourselves, are there any external forces? And the answer is no. There is a collision between these two. They are internal, so momentum is conserved. Is kinetic energy conserved? We have to ask ourselves, is this perfectly elastic? That's the only time that it is. Well, if the bullet embeds itself, that's the definition of perfectly inelastic, so the answer is no. Okay? And is total energy conserved? Well, in a sense, yes. You can't lose the total energy. What happens is, where do we lose the kinetic? It went to thermal energy. And we really can't calculate that unless we subtract it off from the original. Now let's look at the swinging part. Okay? So when it swings up here, that's our second event. Is momentum conserved? Again, ask yourself, are there any external forces acting on our bullet block system? And the answer is yes. There are an external force. There's gravity. So if there's gravity, then momentum is not conserved here. And that's really important. Big no. Then we can ask ourselves, is kinetic energy conserved? And the answer is no. Is total energy conserved? And the answer is yes. we have kinetic energy prime after the collision goes into gravitational potential. So the idea is we can use this to figure out the velocity after right here, and we can use this in conservation of momentum to figure out this. And that's what you're going to do